In the intellectual landscape of the mid-19th century, the science of heat resembled a kingdom divided. On the side stood a powerful and elegant theoretical monarch, the principle articulated by Carnot in his 824 treatise, Reflections on the Motive Power of Fire. His work offered the first successful abstraction of the steam engine, a device transforming industrial civilization, yet lacking a coherent physical theory. Carnot proposed that the production of work in a heat engine was analogous to the work done by water wheel, a substance he called caloric, conceived as a weightless, conserved fluid, fell from a high temperature to a low temperature, generating motive power in its descent. The quantity of caloric remained unchanged throughout the process, a cornerstone of his logic. This framework was beautiful, powerful, and it yielded a profound result, a universal limit on the efficiency of any conceivable heat engine, dependent solely upon the temperatures of its hot and cold reservoirs. For a generation of physicists and engineers, Carnot's principle was the essential guide to understanding thermal machines, yet this elegant conception rested upon a foundation that was beginning to fracture under empirical pressure. Throughout the 1840s, a series of meticulous experiments, most famously conducted by the brewer and physicist James Prescott Joule, presented a competing claim to the throne. Joule's apparatus, often involving paddles churning water in an insulated container, demonstrated a definitive and quantifiable equivalence between mechanical work and heat. The energy expended in turning the paddles reliably produced a specific increase in the water's temperature. The implication was inescapable: work could be converted into heat. The reverse, as steam engines daily proved, was also true. This principle, the conservation of energy, suggested that heat was a form of energy, a mode of motion among particles, and something that could be created and destroyed through transformation. This view stood in stark opposition to Carnot's vision of an indestructible caloric fluid. The world of physics faced an acute crisis. Carnot's theory, which correctly predicted the limits of engine efficiency, required heat to be conserved. Joule's experiments, which were empirically undeniable, proved heat could be generated from work. The two truths appeared irreconcilable. Into this intellectual breach stepped the German physicist Rudolf Clausius. In 1850, he published a paper whose title announced its ambitious scope on the moving force of heat and the laws of heat which may be deduced therefrom. This work was an act of profound intellectual synthesis. Clausius possessed the insight to see that the contradiction was illusory, a product of a single flawed premise within an otherwise sound structure. He recognized the immense power of Carnot's reasoning concerning engine cycles while fully accepting the experimental verdict of Joule on energy equivalence. His paper's central purpose was to harmonize these two monumental insights into a single, cohesive theory. The resolution he proposed was revolutionary. Clausius argued that in any real heat engine cycle where work is produced, a portion of the heat transferred from the hot source is truly consumed. It vanishes as heat and is reborn as mechanical work. The total quantity of heat fails to be conserved. What is conserved, Clausius asserted, is the total energy. This essay will explore the genesis, formulation, and profound legacy of Clausius' 1850 masterpiece. Our investigation will proceed in 3 stages. First, we will dissect the elegant architecture of Carnot's theory, examining the logic of his famous cycle and the critical role of the caloric assumption. We will then confront this theory with the stark experimental evidence for the mechanical equivalent of heat, illustrating the precise nature of the scientific dilemma Clausius inherited. Second, we will delve into the core of the 1850 paper itself. This section will detail Clausius' brilliant modification of Carnot's principle through the introduction of a new state function he would later formalize as internal energy. We will explicate his formulation of what is now recognized as the First Law of Thermodynamics, a principle of universal energy conservation. This formulation resolves the paradox by showing that for any complete cycle, the net heat absorbed by a system equals the net work it performs. Energy is perfectly accounted for, while heat itself is transformed. Finally, we will assess the immense impact of this work. Clausius' paper did more than save Carnot's essential insights. It laid the unshakable foundation for the entire science of thermodynamics. By establishing the first law, it cleared the path for his own subsequent formulation of the second law and the introduction of entropy, concepts that would fundamentally reshape our understanding of physical processes, the direction of time, and the ultimate fate of the universe. The 1850 paper stands as a testament to the power of synthesis, a work that forged a new science from the fragments of a brilliant and incomplete. Clausius' 1850 treatise on the moving force of heat stands as a pivotal moment in the development of thermodynamics. It directly addressed and resolved a fundamental contradiction inherent in Carnot's earlier work on the efficiency of heat engines. Carnot, in his influential 1824 publication, posited a theory based on the premise of heat's conservation within a cycle. He meticulously analyzed the Carnot cycle, a theoretical cycle consisting of two isothermal and two adiabatic processes using a pressure equilibrium diagram to visualize the engine's operation. Each isothermal process involves heat transfer at constant temperature, while adiabatic processes occur without heat exchange. Carnot demonstrated that for a reversible engine, efficiency hinges solely on the temperatures of the hot and cold reservoirs. This relationship, derived from the assumption of heat conservation, provided a powerful framework for understanding engine performance but rested on an ultimately flawed foundation. Experimental evidence, primarily from James Joule's meticulous work on the mechanical equivalent of heat, began to challenge Carnot's assumption. Joule's experiments, conducted throughout the 1740s, convincingly demonstrated the interconvertibility of heat and mechanical work. They showed that a specific quantity of mechanical work invariably produced a corresponding amount of heat, thus undermining the notion of heat's inherent conservation. This created a significant paradox. Carnot's theory, despite its predictive power, contradicted the emerging principle of energy conservation. Clausius masterfully resolved this conflict. He recognized the need to incorporate the mechanical equivalent of heat into a revised theory of heat engines. Crucially, he introduced the concept of internal energy, denoted by U, a state function characterizing the total energy contained within a system. This internal energy encompasses all forms of energy: kinetic, potential, chemical, etc. within the system's boundaries. Clausius' stroke of genius was in reformulating the conservation principle. He stated the first law of thermodynamics, del2 QW, where del2 represents the change in internal energy, Q the net heat added to the system, and W the work performed by the system. This equation elegantly captures the interplay between heat, work, and internal energy. It shows that heat added to a system can either increase its internal energy or be converted into work, or both. Crucially, for any cyclic process like the Carnot cycle, the change in internal energy, del2, is zero. The system returns to its initial state, and any heat added is perfectly accounted for as work done. This statement directly addresses the paradox created by Carnot's theory. While heat, in itself, is not conserved in a cycle, the total energy remains constant, upholding the principle of energy conservation. Consider a steam engine as a tangible example. In a steam engine, heat from burning fuel boils water, creating high-pressure steam. This steam drives a piston performing mechanical work. Clausius' theory explains the engine's efficiency by tracking the changes in internal energy, heat input, and work output. The heat added Q is used to increase the internal energy of the steam delta-U, causing expansion and driving the piston W. The efficiency is determined not by a conserved quantity of heat but by the proportion of heat converted into work, a proportion inherently limited by the temperatures of the heat source and the surroundings. The efficiency is the ratio of work done to heat supply, and Clausius' formulation provides a framework for calculating this ratio, taking into account the internal energy J. Clausius claimed there exists a function of state, U, called internal energy, such that its change in a cyclic process is therefore empirically validated by countless experiments and forms the cornerstone of energy conservation principles. This work had immediate consequences. Engineers could now more precisely model and optimize the efficiency of heat engines. The influence of Clausius' 1850 paper is profound and far-reaching. William Rankine, for instance, built upon this foundation to further formalize the concepts of thermodynamics, and the development of entropy by Clausius himself is directly contingent upon the success of this 1850 treatise, illustrating its significance in establishing the very framework of the field. The first law, as established in this pivotal paper, paved the way for a deeper and more accurate understanding of energy transformations, forming the immutable bedrock of modern thermodynamics and its far-reaching applications across countless scientific disciplines. The implications of Clausius' work extend far beyond the mere reconciliation of seemingly disparate theories. His relentless pursuit of a consistent and mathematically rigorous framework for understanding heat and energy ultimately led to the formulation of one of the most profound concepts in all of science: entropy. This concept, born from the crucible of thermodynamic investigation, provides a quantitative measure of the disorder or randomness within a system. Clausius introduced entropy as a direct consequence of his work on the second law of thermodynamics. In his conceptualization, entropy, typically denoted by the symbol S, represents a fundamental property of a system that dictates the direction of spontaneous processes. The second law, as articulated by Clausius, states that for any infinitesimal process, the change in entropy, denoted ds, is greater than or equal to the heat added to the system, denoted dq, divided by the absolute temperature, denoted d. This relationship is expressed mathematically as ds is greater than or equal to dq over. This seemingly simple inequality holds profound implications. Clausius demonstrated that in an isolated system, one that exchanges neither energy nor matter with its surroundings, entropy invariably increases or, at best, remains constant. This principle suggests that natural processes tend to proceed in a direction that increases the overall disorder of the system. A shattered vase, for instance, does not spontaneously reassemble itself. A drop of dye diffuses through water rather than spontaneously recollecting into a single point. These everyday observations are macroscopic manifestations of the relentless increase in entropy at the microscopic level. Clausius' formulation of the second law of thermodynamics had a dramatic impact on scientists' understanding of the direction of natural processes. Previously, scientists often presumed that all processes were, in principle, reversible. Clausius' work challenged this assumption, revealing that some processes are inherently irreversible due to the increase in entropy. It introduced the concept of an arrow of time, a directionality imposed by the second law. Once entropy increases in an isolated system, it will not spontaneously decrease to its original level. The implications of the second law, as conceived by Clausius, extended even to the ultimate fate of the universe. He posited the concept of the heat death of the universe, a scenario in which the entropy of the universe reaches its maximum value, resulting in a state of thermodynamic equilibrium. In this state, there is no longer any available free energy to perform work, and all processes cease, while the ultimate fate of the universe remains a topic of ongoing scientific investigation. Clausius' vision of a universe tending toward increasing disorder continues to provoke contemplation and debate. The impact of Clausius' work resonates deeply within modern scientific thought. His formulation of entropy laid the groundwork for the development of statistical mechanics, a field that provides a microscopic interpretation of thermodynamic phenomena. Ludwig Boltzmann, building upon Clausius' foundation, established a statistical definition of entropy, linking it to the number of possible microscopic arrangements, or microstates, corresponding to a given macroscopic state. Boltzmann's work demonstrated that entropy is proportional to the natural logarithm of the number of microstates, formally defined as S equals K sub B times logarithm of W, where S represents entropy, K sub B symbolizes Boltzmann's constant, and W corresponds to the number of accessible microstates. Boltzmann's perspective connects entropy to the microscopic behavior of atoms and molecules, providing a powerful tool for understanding the relationship between microscopic disorder and macroscopic thermodynamic properties. Clausius' work also profoundly influenced the development of chemical thermodynamics, a field that applies the principles of thermodynamics to chemical reactions. The second law provides crucial insights into the spontaneity and equilibrium of chemical processes. Chemical engineers employ these principles in optimizing chemical reactions, developing efficient energy conversion technologies, and designing sustainable chemical processes. For instance, the second law sets fundamental limits on the efficiency of heat engines, dictating the maximum amount of work that can be extracted from a given amount of heat. Furthermore, it governs the equilibrium constants of chemical reactions, determining the relative amounts of reactants and products at equilibrium. Clausius' legacy extends into the realm of philosophy, as the second law of thermodynamics raises profound questions about the nature of time, causality, and the ultimate fate of the universe. The unrelenting increase in entropy provides a compelling narrative for the directionality of time, suggesting that time flows in the direction of increasing disorder. This concept challenges the notion of perfect reversibility and raises deep questions about the fundamental nature of reality. Such questions spur intense scientific and philosophical explorations, and they hold a valued place in discourse. In conclusion, Clausius' 1850 paper represents a pivotal moment in the history of thermodynamics. His rigorous analysis resolved the contradiction between Carnot's principle and the conservation of energy, establishing the foundation for the first and second laws of thermodynamics. In doing so, he transformed scientific understanding of heat, energy, and their relationships to the structure of the universe. His introduction of the concept of entropy provided a quantitative measure of disorder and irreversibility, with profound implications for diverse areas of science, technology, and philosophy. Clausius' intellectual legacy reverberates throughout the scientific landscape, shaping our understanding of the universe and its ultimate destiny.